This is the first of two parts. Today we'll talk about quantum annealers, one of two types of quantum computers, the other being the logic gate quantum computers that we'll talk about in a subsequent webinar or tech talk. So just to do a little bit of background, so we're all on the same page, let's talk about our optimization problem types. So we start with the linear program where our decision variables have some form of upper bounds and lower bounds, such as 0 and infinity. We have a linear objective to minimize or maximize. And then we have linear constraints that I've listed as equalities, but we can translate inequalities to equalities, so we can handle any form of linear constraint. And then we gradually can increase the degree of difficulty of our problem from this linear program to a quadratic program where we add a quadratic expression to the objective, or a quadratically constrained problem where we add quadratic constraints, or we can add general nonlinear constraints and turn it into a nonlinear program. And then we can add integer restrictions on some or all of the variables in the model. And then we have some form of mixed integer program relative to the continuous counterparts we just discussed. And then on the spectrum of degree of difficulty for these different problem types, the easiest ones on the left are the linear and convex quadratic problems. So for those, since they relate to conic barrier algorithms, polynomial worst case algorithms are known. Convex nonlinear problems are a bit harder, but still stay to the left of this boundary line, where to the right of which we see the non-convex problems, including all the integer restricted problems and problems with non-convex nonlinear constraints. And, you know, this is where the really hard problems live. And this is where, you know, the potential of quantum computing is really being promoted as possibly being able to solve these problems significantly faster than they currently can be handled. All right, so with that background, to me, one of the sort of challenges when you hear about quantum computing is that you immediately get blitzed with all sorts of new terminology, new notation, new symbols that make it seem that quantum computing methods are completely different from the linear, integer, and nonlinear programming methodologies that we're familiar with. But in fact, that is not the case. And in particular, the quantum annealer, which solves one very specific optimization problem, connects very closely to what we know. And this has potential value or use because you can transform many other optimization problems to this form. So let's start. That's why part one is going to be about the quantum annealer. So with that background, here's our agenda. We will talk about this one special unconstrained binary quadratic optimization problem type that the quantum annealer handles directly, and how to reformulate other integer programs, specifically binary ones, to this form. What we'll see is that there are different categories of this problem in terms of degree of difficulty, and penalty terms play an important role in that degree of difficulty, and making them smaller is an important skill to get better results. Then another aspect of this is that this quadratic problem type has to connect efficiently to the actual annealer hardware. Lastly, I'll go into some misconceptions about really about the state of the art in classical computing, and then we'll wrap up. So the first thing is this reformulation for quantum annealers. So the quantum annealer solves one specific type of problem, namely this unconstrained quadratic binary optimization problem, or QUBO, that consists of every variable being binary, no linear constraints, only the 0, 1 variable bounds that make the variables binary are present, and then a purely quadratic objective function to be minimized. Now, you might say, well, that looks like a very obscure problem type that wouldn't be very useful. But it turns out that you can reformulate constrained binary optimization problems as this QUBO problem type via penalizing constraint violations. So the paper here in this link illustrates how to do this. And the paper has this table that shows how to translate some well-known classical constraints into an equivalent penalty term. So for example, if you have the sum of two binaries is less than or equal to 1, instead of having that as a constraint, you take the product of those two binaries and hit it with a penalty and put this penalty in the objective. So we see that this constraint, excuse me, is only violated when both x and y are 1. So if we put a penalty on the product, we pay a price when it's violated, but not when it's satisfied. And then you look down at the bottom constraint here, and what you can see is that this constraint will be violated when any two of the three variables is set to 1. So we can apply a penalty times the sum of all the bilinear terms in this left-hand side constraint. So here's the example when the left-hand side has 3 variables, but you could generalize that for an arbitrary sum. Now, you might say, well, you're sort of cherry picking the entries in the table in the sense that you chose the ones that had a pure quadratic penalty that fits this pure quadratic objective in your QUBO. If you look at your other ones, you've actually got constants and linear terms. But we will see in the next few slides as we work through examples how to handle those additional cases. All right, so let's now look at a small example and how we would reformulate it as a QUBO. So here we just have a 2-constraint 4-variable problem. And first things first, we'll just minimize the negative of the objective since our QUBO standard form is minimization. And then what we see is that our 2 constraints just align directly with entries in the table. So we just do the penalty term operations. These first 3 terms correspond to the penalty for the first constraint, the last term for the second. We have one thing left to do to make it a pure QUBO, which is to handle these linear terms. But by noting that in a feasible solution, the square of a binary equals a binary, then we can replace the linear terms with a negative sum of squares, and now we have our standard form QUBO. Now, you might say, well, you were lucky there in that example because the constraints in your model align directly with 2 entries in the table. But in reality, you'll have many constraints like the sum of n variables equal to 1, where that's not the case. But we can handle this larger constraint by taking the difference of the left-hand side and the right-hand side, squaring it, and applying a penalty to that. So what we see is either in the case of an excess or a shortfall with this constraint, we will pay a penalty when this constraint is violated. So let's look at the expansion of this term. It can get kind of messy as n grows large. So I like to create this multiplication table that basically is an outer product of the individual terms. And what we see then is that the first terms in the expansion correspond to the diagonal of our multiplication table. We then have this 1 that is the bottom diagonal element. And then we see we have these off diagonal terms that are symmetric. So the terms above and below the diagonal have symmetric counterparts. So we can just take twice the sum of the elements above the diagonal. And then what's left are the bottom row and rightmost column. So we get a collection of linear terms there. Those terms are equal, so we just take twice. Again, use the fact that the square of a binary equals a binary. Rearrange a bit, and now we have our standard form term to put in a cubo for this constraint. A key point here is that these off-diagonal terms, there's quadratic growth as n grows. So this generates a lot of non-zero coefficients in the Q matrix of the cubo. And as we'll see, that becomes relevant in terms of demanding resources in the annealer computation. Now, you might say that, well, you were lucky there too because you had an equality constraint and you were able to, use the square of the differences. But what if you have an inequality constraint? You can't then just square the differences. But what we can do is subtract off a surplus variable to turn it into an equality constraint. We still have some work to do because this is not a binary variable. It's a general integer variable with upper bound as big as n minus 1. But we can address that either by expressing this variable as the sum of n minus 1 binary variables, a so-called unary expansion, or doing a binary expansion based on logs instead, where we reduce the number of variables to 1 plus log 2 of n minus 1. So now we're good to go. We're now back in a familiar form that we dealt with in the previous slide. We can apply our penalty. I won't go through the multiplication table again. The main point, though, is that, again, we have this quadratic growth in the off-diagonal terms. So by adding n minus 1 or even the smaller number of variables associated with the binary expansion, we have increased significantly the number of non-zero elements of the Q matrix, which we'll see later is relevant. So there are some trade-offs between binary and unary expansions here that come into play. All right, so that ends the first section. We'll take a few questions now, but first I want to check with Malahay to see if she has any additional comments.
Thank you, Ed. I just have one comment. If you go back to this slide, I just wanted to say that when we are deciding which encoding to choose, when we are working with classical algorithms, for example, such as Groby, and we wanted to solve a cube with Groby, this decision is probably easy because we say, okay, binary, it has low symmetry and the number of variables is much smaller, so we will go for that. But for example, when we are solving and working with a hardware such as D-Wave or other quantum-inspired hardware that exists, we usually go for the unary encoding because it's very important that we wanted to have a small variation in the coefficients because of the highly limited precision available on the device. So I just wanted to highlight this.
All right, thank you for that. So, are there any questions that we should bring up to the group? We're going to focus on questions about clarity for now, and then we'll try to handle broader questions sort of at the end of the presentation.
I think that for now you can continue. We don't have. Okay, there is one clarifying question. What about X is real? There's a question, what about X is real?
So I think what they're saying is we've shown how to handle binary and general integers. So yes, that is a valid question. How do you handle continuous variables? So you can think about discretizing those continuous variables, but fundamentally, that is a big challenge. I did listen to a recent keynote speech from D-Wave, and they talked about how they have added support for continuous variables, but they did not say how. And I searched a bit and asked ChatGPT and did not find anything that said how they were supporting that. So whether it was just a set of discrete values or something else, I don't know.
Or maybe it's a hybrid approach that they handle those continuous variables using classical algorithms.
Yeah, that could be too. But certainly that's a valid question, and they are aware of it, and they're certainly making an effort to try to handle it. Although exactly what they do and how efficient it is, and whether there's any loss of precision, for example, if you discretize, you're throwing away some feasible values. And also adding a lot of additional variables to the problem, just like with the unary expansion. In fact, I'm going to add one more thing before going on. If you do a discretization, it's almost like thinking about a unary expansion of each binary value between 0 and 1. Okay, so that ends the first section. We've got some building blocks now about how to reformulate into this cubo form. But what we'll find is that these cubos fall into different categories. Sometimes you can actually formulate a model directly as a cubo without having to worry about any linear constraints. In other cases, you have to handle some constraints, but it's very easy to find small penalty coefficients that then address the issue that Malahay raised about wide ranges of coefficients. So you avoid that and are in good shape. And then you have the third or harder category where there isn't an obvious small penalty term, and you need to do some work to try to derive smaller penalties if possible. All right, so let's go through each category. The maximum cut problem is the case of a natural cubo formulation. We could come up with a constrained formulation, but we don't need to. So for max cut, we have a graph with a set of nodes or vertices and edges. And what we want to do is we want to partition our set of nodes into two sets so that the number of edges between the two sets is as large as possible. So we're only counting edges where one of its nodes is in one set and the other is in the other set. So we would not, in this example, count the edge between 4 and 5, but we would count the other one separated by this dashed curve here. All right, so how are we going to come up with a cubo formulation of that? Well, we're looking for binary variables, one for each vertex in the graph, that take a value of 1 if the vertex is in one set and 0 if it is in the other set. So with that definition, if we consider the quantity xi plus xj minus 2xi times xj, what we see is that when the two variables are in the same set, i.e. they're both either 0 or 1, this expression evaluates to 0. But when they are in different sets, in other words, one's 1 and the other's 0, they evaluate to 1. So if we maximize across all the edges in our graph this expression, it will drive the binary variables to take on exactly these values we seek, and the objective will be the maximum cut, and the solution will identify the partition of the vertices. So we have this natural cubo formulation. Again, we use the fact that the square of a binary is a binary to address the linear portion. And we can always minimize the negative of this expression to put it in standard cubo form where we have this maximization here. Excuse me. All right, so that's the first category. Let's move on to the second category, which is constrained problems with natural penalty terms. So we have this undirected graph, again, with a set of nodes and edges. And the goal of the maximum independence set is to find a subset of the vertices where all vertices in the subset are pairwise independent. In other words, not connected by an edge. So in this picture here, the nodes are the blue and gray circles. And then you see the edges. And in this case, the dark blue colored nodes form an independent set because if we look, if you take any pair of these blue nodes, there's no edge connecting them directly. None of them share an edge. So how would we formulate that as a constrained binary problem? Well, what we want is a binary for each node, and we want to set it to 1 if that node is going to be included in the independent set, 0 otherwise. So how do we make the model push the variables to achieve that value? Well, we want everything to be in the set if possible. So we're just going to maximize their sum, but we need to prevent nodes that share an edge from being in the set. So for each edge, we add a constraint that the sum of the edges associated to nodes is less than or equal to 1. And that gives us this pairwise independence condition that we seek. So here is our constrained form. If you look at this picture, which came from an article, it actually related to a map puzzle where you had regions in a map that shared boundaries. The regions were nodes and they shared edges if they had a common boundary between them on the map. Now, there's a bit of ambiguity here in the sense that the article generated edges only for regions that shared a line segment, not a point in common. I decided instead for the model that I would deal with to also create edges as seen by these dashed lines for when regions shared a point. So now, again, our formulation is going to be that we're going to have binaries that are going to be 1 if a node or a region is in the independent set, 0 otherwise. It turns out that it doesn't matter in terms of the optimal solution which way you interpret a common boundary. But anyways, we've got this picture. We've got 58 nodes. We've got the edge set. So it wasn't hard to generate an LP file of this problem and run it on Gurobi. And it turns out that the independent set in the picture was not, which had 16 elements, was not the maximum. Gurobi solved this to optimality in 0.02 of a second. If I use our solution pool feature to enumerate all optimal solutions, that only took 7/100ths of a second. It wasn't clear to me from this article, which was basically extolling the benefits of quantum annealing on these kinds of problems, as to whether this was just an example or whether the idea was that it was significant that the quantum annealer was efficiently solving this. I asked the authors for the larger 250 node models that they had, but so far I have not received any instances back. I suspect that Gurobi can solve those, though, based on my experience with larger independent set problems. Okay, so we've got our binary integer programming formulation of this problem. How do we turn it into a cubo? Well, this one's pretty easy because we can just look up our table and we have this penalty term on the product of the binary variables in our constraints. We can view that as a constraint in the problem. And then we get our cubo reformulation. So here we have our original objective. We have our table that tells us how to create the penalties for each edge in the graph. We again use the fact that the square of a binary is a binary. And we have our cubo. Now the question is, though, what's the best choice for this penalty term? Well, we certainly could use 1 plus the number of nodes in the graph because that basically would ensure that any violation is worse than the worst feasible solution possible. The best solution is just that we can set every variable to 1. The worst solution is we can set no variables at all to 1. This penalty is going to give this a negative objective. So we know that this will work, but can we do better? Well, let's have a look at sort of a little portion, a subgroup of nodes and edges to assess that. So we've got our objective expression down here at the bottom, and let's ask ourselves, well, for this feasible part, what happens if instead of xj equals 0, I decide to set xj to 1? All right, I now have this violation, but what has happened here? Well, I've improved the objective by 1 by taking xj from 0 to 1. So I just need the penalty to ensure that the objective degrades overall. And thus, any value greater than 1 for my penalty term will do the job. All right, so that illustrates that we have, a very manageable penalty term for the max independent set problem. I won't go into the details, but the same is true for the max clique problem because it turns out that the max clique of a graph is equivalent to the max independent set of the complement of the graph. So just to get our terminology down, these red edges in this example are the edges of our graph. And then we have these blue dashed edges are the edges of the complement of the graph. And if you make use of the fact that their union defines all the edges, but they have no common intersection, it's not hard to see that the max clique is equivalent to the max independent set of the complement. So given that that is true, these two graphs share the same vertex set, so we can use our previous formulation, the only difference being that the edge set is now the complementary edge set. So we have our max clique formulation with this one single difference. And now we can just use our previous terminology to derive the cubo in standard form. Again, the only difference being the edge set in the penalty expression here. All right, so that's category 2, binary IPs with a natural penalty term. We'll now raise the degree of difficulty and consider those that lack natural penalty terms and what we might do. And we'll deal with this in equality form. We've seen that we can transform inequalities into equalities. So here's the problem of interest, equality constraints, all binary variables, quadratic expression that could be transformed from a linear expression. And we again penalize the difference of squares and remove the constraints. We have these 3 conditions here. So the first 2 conditions are easy. We can see for any non-zero penalty, if we satisfy these constraints, we pay no penalty. This term evaluates to 0. On the other hand, if we do have violations, we will pay a penalty. So conditions 1 and 2 are easy. The real question is, how do we choose P so that it's big enough so that we aren't attracted to infeasible solutions because they have equal or better objective values than an optimal solution. So in general, there's no obvious choice for P. What we want to look at is how do we sort of get a handle on trying to derive small values in special cases. We already touched on the fact that the annealer has issues with wide ranges of coefficients. So a large value of P can be problematic and actually sort of overwhelm the actual objective coefficients. So they're only trying, with large values, they're basically just purely focused on finding feasibility and not really distinguishing the actual objective that we want to optimize. So we need some methodologies to think about this. Now, at least with D-Wave's annealer, they have some scaling routines that will try to help with this. And lastly, there is an assumption that C and A have rational data that can be rescaled to integer. But for a lot of these sort of well-known NP-hard, NP-complete combinatorial optimization problems, it's really not an issue. You really don't have a wide range of objective coefficients, except for possibly the penalty term. All right, so let's look at set partitioning as an example of a general problem where we might face this challenge. All right, so with set partitioning, we have a master set S that ranges from 1 to some positive integer m, and then we have subsets of S, and we want to collect a group of subsets of S that together whose union gives you exactly S, but the subsets are mutually exclusive. So we create an m by n matrix with column J corresponding to the J subset in our collection. And by column, in terms of the column entries, here's an example. If m is 5 and the column associated with subset J has ones in positions 2, 4, and 5, zeros elsewhere, that corresponds to subset 2, 4, 5. So our set partitioning problem then involves a collection of binary variables that we want set to 1 if subset J is selected, 0 otherwise. we want to minimize some expression of the number of subsets. And then to ensure that we have this unique partition, we take the matrix times the binary variables and set it equal to a right-hand side of all ones. And this will give us a set partition. So we know how to penalize this. We take the difference of the squares of the left and right-hand side of the constraints. And now we find ourselves in this situation of not having an obvious choice for the penalty term. So what can we do? All right, so let's start with an obvious choice. Let's assume that our objective is positive, but it's not hard to extend. Let's just ignore the constraints. Consider the resulting trivial problem and the minimum and maximum possible objectives. Well, we can either set everything to 0 or 1, and the corresponding objective values are 0 and the sum of all our positive objective terms. So we can set P to be 1 plus the difference of those two values, and we have a choice. And it satisfies these three conditions. All right, can we do better? Well, let's think about what we did, because we not only want to do better, but we want to try to do better in sort of an organized way. What did we do? We removed all the constraints, creating an extremely weak relaxation. We then used the maximum and minimum feasible solution objective values to generate our penalty coefficient. Well, let's consider some less weak relaxations. So let's illustrate on a small model. And using our previous relaxation on this model, we would get a penalty term of 13. We can look at the histogram of column counts. And when we do that, what we're really doing is we're aggregating the constraints, the 4 constraints in this problem. And we can use that aggregated constraint as a form of relaxation. Here then is the general form of what we would be doing, where again, E is a vector of all ones. And if we solve this tighter relaxation, what we find is the best objective is 4, so our penalty is now 5. And can we do better? Maybe. What other relaxations are there? Well, let's just solve the LP relaxation for this maximization problem. Turns out that has an objective of 3, so we've got our penalty term down to 4. Can we do better? Probably not on this model, but in general, we may be able to. If we have a feasible solution for our problem, we can use its objective as a tighter value. Or we can look for tighter relaxations than the one we looked at here, like running this maximization problem, the integer programming problem, for a small number of nodes. All right, so we've got this sequence of relaxations that we've generated. Let's try it out on a more industrial strength problem. So I chose T1717, an open MIPLIB model that is pure set partitioning. And if we go through our relaxations, the weakest one yields a penalty term of over 172 million. We then aggregate the constraints and drop it to a little over 2 million. Then looking at the root relaxation, we drop it to 1 million. So that's where we're at so far. But again, we could consider looking for feasible solutions if they can be found quickly. And on this model, that's the case. If we run this model for just 2 seconds, we get this value of just over 200,000. So now we've got our penalty term down to just over 200,000, and it satisfies the conditions. Again, the first two are easy. The point is that for the third one, if you have an optimal solution, you will never, with this penalty term, violate feasibility, even on a single constraint, and get an objective better than that optimal solution, which has no penalties whatsoever. All right, so we've made a lot of progress here. We've gone from over 172 million to just over 200,000. Can we do better? Well, we can sort of, by organized trial and error, tune the different values of P. So, all right, this is just over 200,000. Whoops, sorry. Let's take half of that, roughly half of that, set P to 100,000. Solve it. If it's feasible, we'll either stop or try again with a smaller value and see if we can get a better objective. Or if it's infeasible, we'll bump it up to 150,000. Each one, we can do this multiple times, provided that the annealer lives up to its proposed potential of being much faster than a single branch and bound solve. Otherwise, it's not going to help that much. Now, it's important to remember that the quantum annealer doesn't provide any notion of a dual bound that we use to assess how close we are to optimality. So you may need to run a classical method instead. All right, so in general, set partition problems lack these natural penalty terms. But sometimes they have special structure that enables very small penalty terms. So here's a MIPLIBE 2010 model. I'm not going to go into the details here, but just quickly, the key point is if you go through that drill of going through those different relaxations, you get a penalty of 281. But the point is that going through that drill raises, sort of points you to some aspects of the model that are worth looking at. And if you do that, what you discover is that this model is special in the sense that all the subsets have the same size and the objective coefficients are all the same. And because of that, it turns out you can reformulate this as a max clique or max independent set problem. And once you have that, your cubo reformulation, as we've seen before, has a penalty of 2. So the main point is sometimes you can look at special structure for the model and make additional progress that otherwise you could not make. So regarding takeaways from these different categories, any integer program with rational coefficients can be converted to a cubo, but there is additional work with general integers or inequality constraints. Smaller penalties are better. And again, sometimes you may be able to reduce a model that has seemingly large penalties to one with smaller penalties if you exploit knowledge about the specific model. Again, feasible solutions in the cubo, any solution is feasible to the cubo, but that solution that's feasible in the cubo isn't always feasible in the original problem. And again, it's really about finding a good coefficient for the penalty term. And because of that, tuning the penalty term is sort of a common practice. But despite these challenges, we've already seen some important problems where it's not that hard to come up with small penalty terms. All right, so that ends the section on cubo categories. We'll take additional questions, but first, Malahay, do you have any additional comments to add?
Yeah, sure. I just thank you for that. I just have 2 comments, or no, 3. One, the intuitive idea that you mentioned when you were describing how to find a penalty multiplier for the maximum independence set problem, that the idea here is that we wanted to make sure that the cost that we pay for every unit of violation from feasibility, if just wait until you get there, is going to outweigh the gain that we get. No, not this one, the one that you had with the graph and the maximum independence that you showed that.
Okay, I was just highlighting these conditions
Yes,
in
sure.
general.
Yeah. I was just saying that that intuitive idea is important because it can be generalized. So even if you think of a maximum weighted independence set problem where the vertices are now associated with a weight and the weight is bigger than one, you can use the same idea. Now you can set the penalty multipliers to be slightly greater than the weights of the two vertices that define an edge, and that will ensure that no infeasible solution will have a better value from the optimal solution. Yeah, this part that I wanted to say, that I just wanted to highlight that this intuitive idea, usually based on my experience, helps a lot. That we said that the P here, when the weights are 1, is going to be 2, but if you have weights for them, and for each of those xij, you can have a unique penalty multiplier or a different penalty multiplier, which should be slightly greater than the minimum weights of the WAI and WJ. And also another thing, that those 3 conditions that we have when we are thinking to translate a problem into a keyword, the last one that you highlighted, that we wanted to make sure that the penalty is chosen such that every infeasible solution has, that no infeasible solution cut off the optimal. I think that the point here I wanted to mention is that as long as we can ensure that every feasible solution has a worse objective value than at least one feasible solution, this will be guaranteed. And I think that you touched base on as your last approach of how to find the penalty multipliers. And also I wanted to put into context why we do all these efforts to find the smallest penalty multiplier, because that you mentioned that D-Wave has some scalings to do. When the problem goes on to the hardware, scaling is part of, is inevitable because there are limited precision, that the coefficients need to be mapped to a range, which is +1, -1 for the quadratic terms. And basically, if your penalty multiplier is super big, when you divide it to bring it to that range, your original problem coefficients might get below the noise level, and you end up solving a problem that is not your original problem. So that's why all this effort usually pays off if you try to find the smallest penalty that works for your problem. Yep, that's the comments that I wanted to say.
All right, thank you for that additional information. Are there any additional questions that have been posed from the audience that we should address right now?
We mostly have open-ended questions, so maybe we'll save those for the end. I don't think there's any clarifying questions at this point.
Okay, so Malhay's last comment about, how we need to think about the hardware is not only relevant in terms of coefficient range, it's also relevant in terms of the non-zero structure of the Q matrix in our QUBO and how that connects to the annealer hardware. Now, I want to try to wrap up this presentation right around an hour. So I'm going to skim over this right now. And then after the hour's up, anybody who needs to go can go. And if they feel they want the details, they can watch the recording. But for those who can stick around after the hour, I will come back to this and describe it in more detail. But the point is that while, at least for D-Wave, they make the annealer as much of a black box as possible. And in some cases, you can just give it the QUBO and you're done. That's not always the case. And it's useful to sort of have a peek under the hood as to what's going on, because it can help you basically get more mileage. Just as the same is true with a branch and bound solver like Gurobi. So here's the underlying process. And the first transformation from a cubo to an Ising model is pretty direct, and we'll touch on it, but it's not that critical. But let's do that real quick. So the main point is the hardware actually is better at solving problems with discrete variables that take on -1 and +1. And you again see, excuse me, a quadratic objective term. The linear objective term corresponds to diagonal elements of the quadratic matrix, whereas the quadratic term involves the off-diagonal terms. But the main point is that it's very easy through changes of variables to move from binary quadratic expressions to this Ising quadratic expression, or to go in the reverse direction. So we have these two change of variables here, and you can easily see that they connect binary variables to these -1, +1 values. All right, but there's no real question about resource consumption there. The resource consumption occurs in this embedding phase, where fundamentally the hardware that performs the quantum annealing basically is a collection of graphs with nodes and edges, and the nodes correspond to binary variables. So each binary variable corresponds to one of these nodes in the graph that corresponds to one of these qubits that is, one of the building blocks of the annealing process. And then each off-diagonal quadratic term in our cubo requires an edge in the graph. So basically, the qubits and connections determine the size of the cubo that can be solved. Now, these hardware graphs are far from complete, so that's where the challenge is. How do you map the Q matrix non-zeros to edges in the graph? Now, as the annealers evolve over time, their qubits will increase and their connections will increase that enable them to solve denser qubos. But anyways, the point is that there's a fair bit of work, and again, we'll go into it after the hour's over, in terms of how do I embed my Q matrix sparsity structure into these different graph structures, and what do I do if by default I don't have enough connections to handle it. So we will talk about that, but again, for now I'm going to skip it and just sort of go to the summary. So the summary is, again, 1 qubit per binary variable, and you need a hardware graph edge for each non-zero in the Q matrix. And what this means is you can have 2 qubos with the same number of variables, where one is much harder due to a difference in non-zero count, or they could even have the same non-zero count, but they have different sparsity patterns, and one might be easy to solve and the other might be much harder to solve. Okay, so that's sort of the Cliff Notes version. Again, if you have time and can stick around, we'll go into it after the hour. If you don't have time, we'll have a recording. So let me move to the last section and then summarize. So there are some misconceptions, primarily about classical computing, that I want to go into. So first is the lack of familiarity with the state of the art in classical optimization for these approaches. And that, of course, includes Gurobi and similar branch and bound solvers capabilities. And if you go back to this article that is saying that quantum was really good for these max independence set problems, it talks about simulated annealing as the state-of-the-art classical algorithm. And there's no mention of branch and bound or consideration of it. Now, it makes sense to compare simulated annealing, at least conceptually, as it's the classical counterpart to the quantum annealer. But you don't want to ignore methods that can handle these problems. So there's a tendency to overlook branch and bound, and in particular also overlook its ability to provide this dual bound on the best possible objective value. Our next misconception is consistency in comparisons. So the quantum annealer is really good at handling these QUBOs. You know, the QUBO is aligned directly with the architecture. Gurobi can solve QUBOs directly as well, but Gurobi will typically perform better on the original IP formulation before the QUBO transformation. So you want to compare the quantum annealer QUBO performance to Gurobi on the IP formulation, which is what it's best suited to solve, not the Gurobi QUBO performance. Although if you want to do that just for completeness, that's fine. So that's number one. And I have seen some papers that basically do that. They compare a quantum annealer to a branch and bound solver on the QUBOs, not the original IP formulation. Now, since quantum annealers don't compute dual bound information, you don't want to count the branch and bound time spent proving optimality after the optimal solution is found. So for example, if you have a quantum annealer that runs for 30 seconds and finds a final solution that may or may not be optimal, but let's suppose it is, if Gurobi finds an optimal solution in 10 seconds, but takes 10 minutes to prove optimality, the fair comparison is not 30 seconds to 10 minutes. It's also not 10 seconds to 30 seconds, because at the 10-second mark, you have no idea that this is the best solution you're going to find. The fair comparison is to run each method for 30 seconds and compare the solution, and also recognize that after 30 seconds, Gurobi has some form of dual bound that the quantum annealer doesn't have. And then the last misconception is that even really small NP complete and NP hard problems can't be solved with today's classical computers and algorithms. So Gurobi can solve many such instances to optimality. Even when it can't, it still manages to provide decent solutions within a known percentage of optimality. And going back to this open MIPLIDE problem, which is far from our finest hour, we still see that, you know, after 1 or 2 seconds, we're within 33% of optimal, and then we're within 24% of optimal at the 1 hour mark. And again, the best known objective, though I think it was attained with, you know, a run that went for many, many hours, is significantly better than this. So, you know, we still are doing something. And I should also mention that, you know, this model has over 73,000 binary variables. The current state of the art for qubits on a quantum annealer is roughly 5,000. And the hardware graph has degree 20. On this model, you know, it's going to be really hard to fit 73,000 binary variables into the 5,000 qubits without a lot of decomposition or other, you know, really clever work. And then if you look at the constraints, they all have over 500 non-zeros, which means the logical graph associated with the non-zero structure of the Q matrix in the QUBO are going to have degrees way above 20. And again, if you stick around for the hardware graph connections, you'll see that basically what this is saying is unless, you know, the experts in the quantum annealer community have really come up with a lot of really impressive tactics, I suspect that this problem is currently too big to solve on a quantum annealer. And we'll probably, it will probably be a while before this one can be solved. But again, I'm not an expert in every possible way to, get QUBOs to solve bigger problems. So I may be missing something there. So I'll wrap up, but before I do that, Malahay, any final comments regarding the misconceptions?
No, I think that because we are on top of the hour, we can go to the questions. The comment that I wanted to say, I think that I'll mention it when we are answering the question.
Okay. So let's summarize and then take some questions. So we saw how to reformulate binary integer programs to QUBOs, and we saw that they fell into different categories of varying degrees of difficulty. We saw that general integer variables were more problematic, but you could handle them with unary or binary expansions. There are, at least for D-Wave, which seems to be sort of the quantum annealer that is in use in industry. They have APIs available for direct input of QUBOs. Challenges include that the QUBO has more variables than available qubits, and the Q matrix has more non-zeros than connections in the underlying hardware graph. And that ultimately, in general, relates to that this logical, or synonymously, the adjacency graph of the Q matrix, the more significant topological differences it has from the hardware graph, the more resources you need to embed it in that hardware graph. And then, as Malahay touched on, there's this challenge about limited resolution of distinct non-zero coefficients. But remedies exist. There are API functions or more customized approaches. So things like reformulation and sparsification before transforming to QUBOs. And again, I'll go back into this in more detail after we answer the questions. These minor embeddings in the hardware graph to basically promote graph connectivity. So that's it for today. Again, this is part 1 of 2. We will try to do something roughly a month from now on quantum logic gate computers. And meanwhile, going back to some of the discussions about getting the most mileage out of your limited number of qubits, at our Gurobi Summit in Las Vegas in September, we have a guest speaker who will talk about that. So they may shed light on what to do in some of the challenging cases that I touched on. So with that, thank you for attending. Again, if you can stick around for another 30 minutes, there will be some more detailed material. I'll open it for questions, and while taking questions, leave this list of references up for everybody to see. So questions and any additional comments from Malahay?
I don't have any additional comment. Maybe we can go to the questions.
Okay.
And I'll add my comments to the question.
All right, I'll jump in with the first question. I guess this one's is sort of broad and kind of is about the bigger picture here of why we're even doing this webinar. So the question is sort of, how does Gurobi fit into the quantum annealing landscape? So sort of what's our motivation for doing this webinar? And another related question sort of asks, do we have any plans to deploy any quantum annealing features in the future? Or what's our sort of broader perspective here?
Well, our broader perspective is just that we get a lot of questions like that, and we want everybody to know the basic building blocks. So what we're trying to do here is, I tried to cast this presentation as sort of completely neutral. You see a lot of quantum enthusiasts and quantum skeptics out there. Our view is that it is really too early in the development process to try to, jump into either of those camps. The best thing we can do is make our audience as knowledgeable as possible And so I tried to present this in a neutral way, showing some limitations, but also, pointing out that just as with Gurobi, you don't wave the white flag just because, you hit some limitation in performance. Regarding integrating quantum stuff, Gurobi already has a pretty powerful Cubo heuristic implemented in it. And I'll also mention that at the end of the second part, we will sort of try to go into some of these big picture issues. So there's a teaser for next month's Tech Talk. But again, it's basically, we just want people to understand the nuts and bolts, because as I showed in that first slide, there's sort of this seemingly mysterious language of quantum computing that makes it seem more disconnected from things we know than it really is.
Yeah, I just wanted to add that the QBO at the end of the day is kind of a myth, right? It's a binary problem, quadratic binary problem. It's a problem that Groby and other global solvers have been able to solve. And then in the past few years, definitely we have improved the primal heuristics that we have in Groby for handling QBOs. And regarding that, is there any plan to do kind of quantum annealing with Groby? I guess we don't have such a plan, at least as far as I know.
Yeah, I think the quantum annealer companies are more likely to, do that integration. For example, just run an LP solver to get a dual bound after the quantum annealer comes up with, a hopefully good solution quickly.
Yeah, but I think that the other point to highlight is that the quantum annealer or these devices, regardless of how many more qubits they will have in the future or how their connectivity will improve, inherently are heuristics. So they just give
Yes.
one feasible solution. So, and they completely fall in another category of the optimization solvers, while Groby is a global solver. And of course, and it always gives you a sense of how good or bad your solution is.
Yes, I agree with that. But at the same time, I had a conversation with one of our founders who has talked with some of the people in the quantum camp. And what he told me is something that I think is reasonable, but I'm not sure, which is the underlying physics of the annealing process should find good solutions, even though it's a heuristic. So it's not like it's a random heuristic that doesn't care about the objective.
Yeah, that's true. That's true that basically the adiabatic quantum computing should give you the ground state of the problem that you are casting to solve. But I think that there are some physical limitations. For example, how slow the annealing is and how accurate the coefficients are presented, yes, and all those kind of things. But the theoretical proof is there in terms of that it will give you, but providing the physical condition for that theoretical proof to kind of come along doesn't still exist, but it might improve in the future.
Okay. I think that's a good way to frame it. Yeah. Next question.
Okay, so our next question we have here, which is related, is which kind of known combinatorial optimization problems can be solved with the current quantum and classical hardware more efficiently via D-Wave formulated as a QBO compared to a classical MIP solvers formulated as a MIP?
So I don't think there are. I mean, you really should ask D-Wave that, but I think some of the papers at the bottom of this are indicating that so far the number of qubits and the size of the hardware graph is such that for the most part, classical optimization is still ahead.
Yeah, I think that I just wanted to add things. Basically, theoretically, you can map every MIP to a QBO, but this definitely comes at a cost. And also in terms of the size, because when we do this penalization of the constraints into the objective function, we make the problem fully connected, right? We connect every nodes to another, every variable to another variable. And then, for example, on the latest chip that D-Wave has, one of the latest, I think, Advantage, because they had Advantage and it has almost 5,000 qubits. As far as I know, the biggest complete graph that they can embed is around 150. So the size is still very limited, 150 variables. So, and the people who go and solve these big problems using D-Wave, usually they use decomposition approaches, but also I'm not aware of very clear example of that the quantum device has given solid performance boost compared to the classical solvers. There is a type of problem that the statistical physicists use called the spin glass problems. They do most of their benchmarks on those type of problems. It's a kind of icing problem, but there are different types of the icing problem depending on the topology of the graph, 2D spin glass, 3D spin glass. On a complete graph, they're usually in the quantum physicists or the statistical physicists use those benchmark problems to measure how much, for example, the hardware has improved from one generation to the next generation.
Okay, and if you listen to Malahay's comment, you might be asking, well, wait a minute. She said 5,000 qubits. There's one binary, each binary requires a qubit, but the biggest problem they're solving was only 150 variables. You might ask, well, what happened to those other 4,800 plus qubits? And the section I'm going to go into in more detail momentarily will answer that question about what other aspect requires those qubits to be devoted elsewhere. Okay, I'd like to take maybe one more question and then go back to the embedding and then handle any additional questions after that.
Okay, I'll ask one more. So they're asking, so they say, given the growing landscape of Ising type solvers like D-Wave, Fujitsu's Digital Annealer, Hitachi's CMOS Annealer, which technology direction do you see as most promising for solving large-scale problems? Maybe one of these methods or methodologies or hardwares, or maybe some kind of hybrid approach with quantum plus other technologies.
Yeah, again, there's this broad spectrum, from quantum is not going to do anything to quantum is going to solve everything to all these in-between cases. And again, it's too early to tell in my view. I also really only know about the D-Wave annealer, so I can't comment on some of those other architectures and what their perceived advantages or disadvantages are. Malahay,
Yeah.
anything?
Yeah, I also cannot. Yeah, I agree that the time will tell, but the other solvers that you said, they are not quantum. They are classical hardwares that, for example, different types of Monte Carlo simulation algorithms, such as simulated annealing, parallel tempering, all implemented on those devices. For example, Fujitsu device use FPGA to implement those algorithms. It's not a quantum device, but the future probably will be a hybrid approach to solve larger scale problems that maybe the solution that the quantum gives will be good enough as a reliable primal heuristic that can speed up the time that we need to close the gap. But definitely connecting these two things will be hard, or if at some point we can come to a sort of algorithm for solving QBOs on a quantum device, not annealer, for example, for gate that gives us some proof of optimality, we can use that as a subroutine in some of the Groby procedures that we have. Because as long as it's just a heuristic and doesn't give us any proof that the solution that we get is optimal, we cannot use it as a sub procedure for pruning things or for branching decision and all those kind of things.
Okay, let's pause the questions. I'm going to go back and I want to touch on, because it came up in some of the questions, either directly or indirectly, how do we embed the non-zero coefficients of our Q matrix into the hardware graph. So this embedding step that sits under the hood. And we talked about these graphs. So let's now dig down. So we'll start with sort of one of the simpler graphs, which has since been replaced with more sophisticated graphs on the more advanced machines. But this one's the easiest to sort of picture. So the Chimera graph basically has collections of 4x4 bipartite graphs that comprise this notion of a unit cell. So each unit cell has the 4 connections for each node that is a qubit to the four elements of the bipartite complete graph. So we see bipartite complete graphs here in each unit cell, and we have those connections. And then we'll talk about a bit more subsequently. There also are some connections between the unit cells that we can exploit as well. So in terms of embedding non-zero structure into this graph structure, it's important to note that even the complete graph of size 3 is not a subgraph of these 4x4 bipartite complete graphs. So we have some work to do. We can't just immediately embed even relatively small portions of the Q matrix into this graph. So again, the key points are binaries mapped to a single qubit, and each off-diagonal quadratic term requires a connection or an edge in the graph. And ultimately, it's the qubits and connections that determine the size of the QUBO that can be solved. And, you know, as the Annealers increase their qubits and connections, they can solve larger QUBOs. All right, so I'm sort of recasting the Chimera graph and these 4x4 complete bipartite graphs into an equivalent topology that I think is a little easier to handle. So here we see our unit cells and their internal connections, and then we see the intra-cells, intercell connections in blue here that connect one unit cell to another in a limited way. So the question is, how do we map a non-zero, a subgraph associated with the non-zeros of the Q matrix into these unit cells along with their intercell connections? So what it really relates to is how similar is the adjacency graph, also called the logical graph of Q, to this hardware graph. That's what we need to get a handle on. The more related it is, the easier it is. The less related it is, the harder it is. So here's our unit cell. If you have a portion of Q that induces the following subgraph, where it's basically the unit cell plus a couple of edges, that's going to be pretty easy to handle. But on the other hand, if you have also just 8 qubits, but they form a complete graph, well, then the embedding process is going to be more difficult. And let's have a look at what our strategies are. Now, again, the Chimera graph is, an older graph. The more recent graphs, like the Pegasus graph, have more connections. Instead of four connections within the units cells, they have 6, and they have 9 connections between cells. So this is an advancement that improves the connectivity, but the challenges remain. The graphs will continue to improve. They now have a Zephyr graph, which is even more connected. And the APIs are capable of, doing some mapping work to the hardware graph. But you still have these situations where the APIs are not enough to just rely on internally. What do you do then? All right, so we've got two plans here. The first is we're going to reformulate our QUBO into manageable subproblems with fewer differences between the logical graph. The second, although it typically needs to be done in the first case, but the second is to do additional minor embeddings in the graph where we basically connect qubits to create additional connections. And we'll talk about how to do this. But this consumes resources. And even though there's API calls to facilitate the process, you potentially have to do some of this yourself. So let's just briefly go into this. So let's go back to our familiar set partitioning constraint. And here we see how we created our penalty term and how we have this quadratic growth in the off-diagonal penalties. So suppose we have a set partitioning constraint with 9 variables in the left-hand side. We've got this quadratic expression that basically generates a complete graph of size 9. That means we have to embed in the hardware graph. We have a maximum degree of 8. That means we have 36 quadratic terms. All right, so our Pegasus graph has degree 15. So an efficient embedding is going to be pretty easy. But if we bump up the number of variables in our constraint to 20, we still have this quadratic sized expression of penalty terms. Now the max degree is 19, and we have, 190 quadratic terms. The Pegasus graph has degree 15. So now we've got some work to do. We're not just going to be able to fit everything in and not worry about it. But plan A says, well, let's reformulate. So this constraint up here with 20 variables, all binary summing to 1, can be replaced with these 5 constraints. So basically, I break up my 20 binary variables into 4 groups of 5, assign them to a new binary variable, 1 for each constraint of this type. So I add 4 new binary variables, and then add a constraint that the sum of the 4 new binary z variables equals 1, and any feasible solution for our original constraint will be feasible for this 5 constraint expression and vice versa. But now let's think about how we would embed the penalties, thinking about how we would penalize these constraints. And what we have is for each of the first 4 constraints, we have a max degree of 5 and 15 quadratic terms. We have 4 such constraints. We then have our last constraint with a max degree of 3, which yields 6 quadratic terms. So a total of 66 total quadratic terms to embed with a max degree of 5 at the expense of 4 more variables. So this is a favorable trade-off. By reformulating, we make the process of embedding that much easier. Now let's talk about what happens if we actually need to use these minor embeddings. So let's take a look at a specific example. I'll illustrate with the Chimera graph because it's simpler. So we have this unit cell here, which is this 4x4 complete bipartite graph. And we want to embed a subgraph of the logical graph associated with the Q matrix that is complete. how do we do this? Well, we have all these edges that I've highlighted in red in the unit cell that are not connected in a single unit cell. So what can we do instead? Well, we make use of the blue connections that go to the neighboring cells. So here's an example. We have 8 binaries and their associated qubits. And now we have this complete graph we need to embed. So we've got these additional edges that we need to account for. So we will use the neighboring horizontal unit cell, and I'll illustrate for this qubit and variable x4. So we use a neighboring connection and assign another qubit also to x4. Now we need to strengthen the connection because we need these both to evaluate to the same value during the annealing process. So there's an API call to connect these qubits together. What have we accomplished now, though? Now we've opened the door for x4 to, in this adjacent cell, it does have connections to x5, x6, and x7 that were lacking in the original unit cell here. So at the cost of an extra qubit being assigned to the same variable, we've now addressed the connections needed for half of our complete graph. We can deal with the other graph by doing basically the analogous task for one of the vertical neighbors, and we can take care of the other variables here, x0 through x3, and that's how we do it. So there's a cost here because we've duplicated qubits, but we've gained something big because we've now managed to create additional connections. We're using additional resources, and the other thing is longer chains become more problematic, not only in terms of additional qubit consumption, but there's a physical process underlying them that makes it more challenging. And fundamentally, the amount of embedding we need to do increases as the differences between the adjacency graph of Q and the hardware graph increase. So that's the sort of deeper dive into the embedding process. And that also explains why, you have models with 5,000, or you have annealers with 5,000 qubits, but the size of the model you can actually solve on them is significantly less. So with that, I'll open it up to final questions and any final comments from Malahay.
Sorry, yeah, sure. I just have one comment about the embedding that you mentioned. You mentioned 2 approaches. I wanted to say that in both approaches, embedding will be unavoidable because the whole idea of embedding is that we have a logical problem or the original problem, and now it has a different graph structure, and now it needs to be mapped on the hardware that also has a different graph structure, and that hardware graph is very, very sparse. The whole process of embedding is that we are going to use embedding to represent each of the variables that we have in the original problem by a chain of qubits on the hardware. This is basically called embedding, and then also we need to make sure that we adhere to the all connectivity that exists on the original problem. So, and there are different algorithms for finding this embedding. Originally, embedding and finding the embedding for a graph on the hardware graph is an NP hard problem, but if you know the logical graph in advance, there are some algorithms for polynomial time algorithms for some graph types. but we usually use I think DV has APIs that they are using heuristic algorithms, and sometimes you might not be able to find embedding. So, and the approach one that Ed was talking about can basically helps you if you decrease the number of, if you decrease the connectivity or the degree, can be more successful in finding an embedding for your problem. And also another important factor that makes the approach one something to think about when trying to solve something on a D-Wave machine is that when you do embedding and we are going to represent each of the variables with a chain of qubits, the number of qubits that we use to represent each of those variables is called chain length. And experimentally, it is acceptable, or it's found that the smaller the chain length, the better. And then if you have a basically a formulation that has less degree, you can have an embedding with a smaller chain length. So this is another reason why using approach one might give you some advantage if you can do this reformulation. But I just wanted to say that embedding will be there, and it's very rare that you find a problem that just directly maps on your hardware graph structure.
Right. So the only way it directly maps is if the logical graph with your Q matrix is actually a subgraph of whatever hardware graph you're working with, correct?
That's true. Yeah.
That's the only case you won't have to do some embedding. But if it's close, either directly or after you do some of those decompositions, the chain length is going to be much less than if it's totally different.
Right.
Okay, let's open it up for any final questions, and then let's wrap up.
Yeah, we can perhaps have a final question. So the question is from a person that works in the logistics and finance sector, and could you highlight the main differences between quantum annealing and classical optimization in practical terms when it comes to solving time, problem size, and result quality?
Unfortunately, I think the answer is no. We did talk a little bit about how, so far the classical optimizers seem to be doing better on most of the integer programming optimization problems. But at the same time, given what we discussed, hardware graphs are going to continue to improve in terms of connectivity and qubit size. So I think, the point is not to talk about where things stand now. The point is that there is potential for things to change. But again, there's this wide spectrum ranging from, quantum annealers will have little impact on the kind of optimization problems that Gurobi solves to they will have a really big impact to everything in between in terms of hybrid approaches. So we're trying to really avoid speculating. I will, though, again go back to the reference section. So yeah, one of these, a few of these last few papers, I think, do have some benchmark results. And I think based on those results, again, for the moment, classical is still working better for most of these problems.
And also I wanted to mention, especially if you have a problem that has continuous variables, that is very common in the real world problems, and usually real world problems are highly constrained. So usually mapping a problem to a QUBO, which is very less expressive and restrictive than a MIP language, comes with a huge cost. So to answer the question, if you wanted to solve your problem today, I would say classical algorithms definitely provide better results, given all the evidence that we have. But what is going to happen in 5 years or 10 years, I'm not sure.
Okay, maybe that's a good stopping point. And then also for these sort of far-reaching questions about landscape and stuff like that. Again, at the end of the second part 2 presentation, I will try to talk about those a little bit. So there will be an opportunity to return to the broader questions at that time.